Hello and welcome to this lecture. My name is Mira Kochibuto Marcel, and I'm the founder and the director of the Pan-African Citizen Science E-Lab. So today we are going to be learning about solar wind and aurora. Solar wind and aurora. So as a gentle reminder, this lecture is being sponsored by the Free Astroscience. So back to what we say that we're going to talk about, the aurora, solar wind and aurora. You probably have seen this kind of pictures from the internet, or probably you are lucky enough to have it in your up above your skies if you live in such places. So you probably have seen these beautiful pictures. They are not rainbows, and they do not form through the process that forms the rainbow. They are different process. Okay, the the sky suddenly becomes very colorful. So we call that the aurora. Okay, it's called that the aurora. So we want to know the science behind this. We want to understand what is going on. We want to understand the science behind this. Beautiful. It makes the sky to look so heavenly. So here is some picture taken from the International Space Station. So you can see from the ISS, you can see the beautiful aurora, and the green is always very prominent. So at the end of these lectures, let us should be able to explain what the sun is and why it is made up of plasma. We should be able to describe what solar wind is and where it comes from. You should be able to explain how auroras are formed and identify the different types and shapes of aurora. And you should be able to describe auroras beyond Earth on the other planets. So we're going to start from the sun. The sun, our sun. The sun is a star. Well, that is a lesson from another day. So from this simulation, you can see this is the sun, and here is the Earth orbiting the sun, and here you see the moon orbiting Earth. Okay, this is very significant for what I'm going to be saying next. So whenever you hear about the sun, can you can you think about the uses of the sun? What are the uses of the sun to us? What are the importance of the sun to us? So I'm going to mention a few of them. For instance, number one, the sun is our natural, it's our is our it's our source of natural light. Okay. For instance, it helps us to set between day and night. We know the day is when our Earth's surface is facing the sun, and nighttime is when we are facing away. So it is the sunlight that provides natural light for that. Okay, no amount of city light can replace the natural light that the sun provides. So that is number one important use of the sun to us. Number two is a source of heat. Is a source of heat. For instance, we have liquid water. We have substances in liquid form because of the heat from the sun, even gas too, but liquid water. Okay, if there were no, at least the water is the most useful, one of the most useful substance material to us because we survived using water. Okay, now if not because of the sun, if our planet suddenly becomes a rock planet one day, you know we will be cut off from this natural source of heat. So our planet will become frozen, and all living things are going to die. Do you understand? So liquid water is possible because of the sun. And also, it makes the temperature of our environment comfortable. Like not too cold and not too hot. It makes the temperature to be comfortable. And life, the heat from the sun is very important for the existence of life on Earth. Very important. If not because of heat, we would not have been here on this planet. So, number three, the sun is important because it supports life. Things like photosynthesis, you know, plants use the solar energy for food production and also for some chemical reactions that happen in trees and green plants that release oxygen. So the sun is important. Solar energy is important for that. It's important for climate and weather control. The sun drives the winds. The sun ensures rainfall, and also ensures ocean current. It drives the ocean current. The sun is important for energy generation, the cleanest energy ever. Like it converts solar energy to electricity, which we use for heating, we use it for charging devices, we use it for industries and powering our devices in general. The sun is also very important because it gives us vitamin D. It helps our body to produce vitamin D, okay, which is important for strong bones and healthy immune system. We also use the sun for navigation in ancient days, even now. Okay, for instance, the sun rises from the east and sets at the west. So wherever you are, whether in the sea or on the land or in the air, you can use that to understand direction. So I can go on and on and on to mention the different uses of the sun. Okay, but the sun is much more than that. It is the sun that makes those beautiful skies that I've just described possible, and I'm going to explain how. So first of all, the sun. If I might ask you, what is is sun solid or liquid or gas or none of the above? If you only had basic science knowledge, you would say, oh, maybe it is liquid, or maybe most of you are going to just say liquid. Okay, but no, the sun is none of them. The sun is not a liquid. The sun is not a solid, it is not a liquid, and it's not a gas. The sun is made up of plasma. It is a giant ball of plasma, and I'm going to demonstrate it via this video. The sun is a giant ball of plasma. That is the sun, a star. That is how most stars are. All the stars are like this, plasma. So take note of that. So what is this plasma? What is this plasma? So to understand what plasma is, let me take you to the states of matter. From your basic science, you learned about solid, liquid, and gas as the three states of matter. Okay, so but there are others. Okay, but in this lecture, I'm going to show you the fourth state of matter, and I'm going to use water as my basis because it is most common. So imagine that you have a water ice cube. So it is in the solid form. Okay. Now, when you apply heat to that ice, it begins to melt. When it melts, it turns into a liquid. Okay. When you continue heating that liquid, water, some of them will evaporate. That evaporation, the evaporated water are gas. But at the boiling point of water, all of them becomes gas. So we now have solid, liquid, and gas. Now the question comes: what if I keep heating that gas? What will happen to it? I've asked that question when I was when I was still in secondary school, and no one could give me the answer. And now I want to give you the answer. The answer is if you continue heating a gas, vapor, water vapor, if you continue heating it, it turns into a plasma. It turns into a plasma. So that is the fourth state of matter. So what then is this plasma? Plasma is a state of matter made up of charged particles like electrons and ions. Okay, remember when you have an atom, when an atom when atom loses an electron, the electron is negatively charged. Remember, when an atom loses an electron, it becomes a positive charge. The electron is negatively charged, and when an atom gains when an an ion, a charged uh, atom, gains an electron, becomes negatively charged. But for the sake of this topic, I'm going to focus on the atoms that lose electrons. So they lose their electrons and becomes ion. Okay, so a plasma is a state of matter made up of charged particles formed when a gas is given enough energy when a gas is given enough energy to break its atoms apart. So when you give a gas, a substance that is in a gas form, if you give it high enough energy, it is going to lose all its electrons to become an ion. So that is the process of breaking the atom apart. Okay, so you can see that this plasma is the fourth state of matter after solid, liquid, and gas, right? And it occurs at a very high temperatures, the kind of high temperatures that only the stars can provide. Okay, okay, you can also do them in the lab. Like this simulation you can see there is from the lab. You can also have them. But if you want to produce a huge quantity of plasma, you're going to need a lot of energy, and that energy are the kind of energy you'll find in stars. Okay, so that is, you have these free electrons and you have ions. Okay, now the sun is very massive. Okay, so its gravity is insanely massive. It is very massive, so it traps this plasma. Okay, just the same way gravity traps everything around us. If you jump up, you fall down. Everything that goes up without an aid will fall down. So gravity is keeping everything together, is pinning everything on earth. So in the same way, the strong gravity of the sun is keeping everything glued to the sun. So now there are a lot of things that go on. This plasma is all over the sun, right from the center of the sun to the surface. Okay, so there's a kind of a convection current that goes on in the sun. Okay, that's kind of convection current. So soup, when this soup of plasma makes it to the surface. Okay, when they make it to the surface of the sun, when they make it to the surface of the sun, the temperature at the surface of the sun is very high. We call it the corona. So this corona has high temperatures that gives these charged particles enough energy to escape the sun, and so they form the solar wind. So the escape of these charged particles from the surface of the sun constitutes our solar wind. Okay, so remember, like air, we say air and we say wind. What is the difference between air and wind? It's simply air is just a mixture of gases, right? But wind is air in motion. So when these charged particles are exiting the surface of the sun, they become a solar wind. So here's the picture that describes everything that I've just talked about right now. So here are the charged particles, the electrons, the ions, so they become solar wind. So here's the corona. At the corona, the temperature is very high, allowing the particle to escape sun's gravity. So what is this solar wind? I want to define solar wind. So solar wind is a stream of tiny charged particles, the protons and the electrons, or you can call them ions and electrons, that flow from the sun into space. So I'm going to play that video again so that you can see it the second time. So all these things that you are seeing here flowing out, you can see the surrounding of the sun. They are the wind, solar wind. So these are the solar wind. Solar wind. So these are what we call the solar wind. Take note of that, the solar wind. Now, we have two types of solar wind. We have the slow solar wind. They move at a speed of about 400 kilometers per second, and they come from the quiet region of the sun. And we have the fast solar wind, which move at a speed of about 800 kilometers per second and come from the dark areas called the coronal holes. Now I am done with the sun. I've explained the meaning of plasma and I've explained solar wind. Okay, now let us come to Earth. Let us discuss about the Earth's what is going on around the Earth. So the Earth has a magnetic field. Okay, not that there's a magnet at the center of the Earth. Okay, you know the Earth interior is made up of metals that are in molten form. Okay, so once they are in molten form, they the movement of charges, electrical charges that are in molten form will constitute a magnetic field. That is physics. Okay, so their motion gives the Earth an overall magnetic configuration. So uh, that is why Earth has a magnetic field. The magnetic field, we call it a global magnetic field. Okay, just like we have geographical north and south. This is the geographical north. This is the geographical south. Okay, the magnetic field also has poles. We have the north magnetic pole and the south magnetic pole. Okay, they are not the same. They are not in the same position. There's an angle between the two. Okay, and these magnetic poles also change. Do you understand? They also change. So, this magnetic field creates a protective bubble called the magnetosphere. Now, when the solar wind reaches Earth, depending on the direction they encounter the magnetosphere. If they enter through the sideways, if they encounter the magnetosphere through the sideways, they are knocked out. They are redirected to, they are just redirected, okay? But once they enter through the poles, they are redirected into the earth. So that is why those, at the poles of the earth, that is why we see corona. These are, we see the aurora there. So those ones that enter through the poles help to form the aurora. So that is why we don't see the aurora no countries, no region that live here see the aurora because the charges that would have excited the atmosphere have been knocked out. So most of the solar wind are redirected to the universe. So that is what protects our Earth. It tries to protect our Earth. Okay. So here is another diagram that describes the direction. So when the solar wind comes from the sun, the magnetic field of the Earth helps to redirect it, protecting us. It is also protecting our atmosphere. I'm coming back to that. So now let me explain why the aurora appear at the poles. I've talked about it. So here is the aurora appearing at the poles. So here's the northern hemisphere, and here is the southern hemisphere. So like I told you, the Earth magnetic field, the field lines, they end up in the poles, okay, near the poles, not, the near the geographical poles, okay. They end up there, and these solar particles are guided there. Do you understand? So that is why countries in the northern and southern hemispheres like Canada, Alaska, Antarctica, they see aurora. But countries in the middle, like Africa, we don't usually see the aurora. Okay, Africa and other countries in the equatorial regions do not experience the aurora. Now, let me describe the physics of the aurora, the physics that make the aurora possible. Now, when these charged particles, when they enter through the poles, okay, they encounter air in the upper atmosphere. And air in the upper atmosphere is a mixture of gases like oxygen, nitrogen, and so on and so forth. At least those ones are the predominant ones. They are neutral, okay? They are just happy. But when they encounter these energetic particles, these energetic ions or the electrons, they collide, okay? And when they collide, this energy from the ions and electrons excite. They make the atoms, sorry, they make the electrons in these air molecules to be excited. I mean, they go up in the higher energy level, and once they're in a higher energy level, they will come down to the lower energy level. And the process of coming down, they have to give up some energy until they become, the way they were before. So that giving up, that energy they give up, is emitted as light, and that is what we see as the aurora. So that is just excitation of molecules in the atmosphere, the excitation. So now, this aurora do not stay, this is a picture, they do not stand still, okay? The real auroras, they move like waves, they move like ripples and waves in the atmosphere, and this is described as the aurora dance, okay? Aurora dance. And the reason why they move like that is because the earth magnetic field is not rigid, and also these solar winds follow that are being redirected by this earth magnetic field. So that is why there is some sort of motion. That is why they are moving in all, performing all kinds of movements. So I want you to watch this video. I want you to watch this video, watch very carefully the motion of the aurora, and also observe the color changes, the beautiful color changes, because I'm going to talk about the colors in my next slide. You can see the beautiful colors. You can see green, you can see red. You can see blue there. Video is very long, but I'm going to just cut it short, okay? So the video is very long, but I hope you have understood what I'm trying to describe. Now let me describe the different aurora colors, okay? Now these colors come from the different types of gas in our atmosphere. Our atmosphere is predominantly made up of nitrogen and oxygen, okay? Now oxygen produces a green and red auroras, okay? So it is oxygen. They produce these two different kinds of color depending on their altitude. For green aurora, oxygen levels are between 100 to 200 kilometers. When they are excited, they produce green aurora. But oxygen above 200 kilometers, when they're excited, they can red aurora. So that is why these two, we have these green and red auroras. But for nitrogen can produce blue, it can produce purple, and sometimes can produce pink. And they are usually seen at the edges of aurora during strong solar storms. So these are the colors I've just described now. The beautiful colors, very beautiful colors. Now, types of aurora, we have two types of aurora. We have the aurora borealis and we have aurora australis. Aurora borealis is in the northern hemisphere, the kind of aurora you see there. It's also called the northern dawn. Usually seen in countries like Alaska, Finland, Iceland, Norway, and Russia. These are the places you see them. And we have Aurora australis. You see that in the southern hemisphere, like in the Antarctica, southern New Zealand, southern Australia, and southern Chile. So those are the two types of auroras we have. Now, auroras have different shapes. We have the ones that look like curtains, okay? This one looks like a curtain, which is the most common shape of the auroras. So they look like they look like glowing waving fabric in the sky, and are caused by particles following the curved magnetic field lines. And we have the arcs, one that look like an arc. They are very smooth and curved bands of light, often stretched across the sky from the west to east. Sorry, from east to west. And they usually appear before the big auroral display. Then we have the one that look like rays and the one that looks like spiral. So the reason why we had these kinds of shapes is of because of the magnetic field of the Earth. Okay, so because of the movement of the magnetic field of the Earth. Now, auroras are not unique to Earth. Other planets also experience it, even in a more high level. So take for instance Jupiter. Jupiter is the king of auroras. Okay, Jupiter is the biggest planet in our solar system. It has the strongest magnetic field of all planets. It also has a thick atmosphere, and just like Earth, it gets a constant flow of charged particles, the solar wind. Okay, these three combine to give Jupiter an aurora that is hundreds of times more powerful than Earth. They are so bright that they glow in the UV and X-ray spectrum. Okay, and also Jupiter's moons like Io, they are volcanic. They release these volcanic gases, and the magnetic field of Jupiter traps those gases, and it feeds it feeds its giant aurora, and makes it even bigger and brighter. So then we have Saturn. Saturn also has a very powerful magnetic field and a thick atmosphere. So its aurora looks very smooth and elegant. Look at this aurora, and it also changes with solar storm. And here is Uranus and Neptune. These are very weird planets because they are tilted and they are very unusual. Okay, so their magnetic field are tilted and off center, and that creates a very strange twisted aurora. So that is why the aurora sits neatly over the poles. They don't sit neatly over the poles, and they appear in unexpected places. For instance, this is Neptune, this is aurora, and that is Uranus and this aurora. So they don't sit at the poles, just like other planets. So in summary, for aurora to exist, a planet must have three things. It must have an atmosphere so that so there are gases to glow. This is must have an atmosphere. It must have a magnetic field to guide the particles towards the poles. Remember that the atmosphere, this magnetic field is what guides its atmosphere. This magnetic field guides its atmosphere. Without the magnetic field, there will not be an atmosphere. Okay, then it has to be orbiting a star. For instance, Earth orbiting around the Sun to get a supply of solar wind. So Mars has almost no aurora because Mars has a very thin atmosphere. The atmosphere of Mars is just 0.1% of Earth, and it almost has no global magnetic field. So that is why it cannot create a strong aurora. In fact, the solar wind strips away Martian atmosphere. Like I told you, because it doesn't have a well-defined global magnetic field, so the solar wind just strips it away, strips the solar the atmosphere away. So that is why Mars does not have an aurora. So how about rogue planets? Can rogue planets have aurora? Rogue planets are planets that are not bound to any star. They're just roaming about the universe. So they may probably have a magnetic field, and which also can protect the atmosphere. But because they are not orbiting a star, they cannot have aurora. So, ladies and gentlemen, that will bring me to the end of my lecture today. You can share your questions in the comment section. Thank you so much.